Alright, so in this video we're going to continue in section 4.4. We're going to look at page 294, problems 97 through 100. This would probably be a good time to pause the video, grab your book, look on page 294, and before we actually complete problems 97 through 100, at least look at them, read through them, put your minds around what we're being asked to do so that you understand how we're going to proceed. Okay, so we're told in this problem that we're given a position function for a particle that's traveling along the x-axis. So this particle is just going left and right, back and forth, and that's the motion. It also tells us in the information above the problem that this is the position for the particle and that x prime of t is its velocity. We understand that. And then it also gives us an integral of the absolute value of that velocity, and it tells us that that's the distance the particle travels in the interval of time. So here's our time interval. We're only considering time between 0 and 5 seconds, and this is the position at any of those times. Okay, so our objective in 97, given this position function and this interval of time, is to find the total distance the particle travels in 5 units of time. Well, we need to consider that the particle may have traveled left some steps and traveled right some steps and then maybe back left and back right. So we've got to add all the steps. We're not interested in this problem in its position at any time t, but just in the total amount of steps it takes going left and right and how many steps that was. Okay, so it tells us that we can use this integral a to b, absolute value, okay, of the derivative. And that would give us the amount traveled. Okay, well, to find this answer, we could certainly do it all on the calculator. We could find x prime of t, the derivative. We could type that into y1. And before you type it into y1, you might want to include in y1 the absolute value. So it would look something like y1 equals absolute value of the derivative of this equation. You can go to the home screen and perform the necessary keystrokes to find the value of that integral. And that would be easy enough to do it all in the calculator. But let's just go forth by thinking that, well, what if we don't, have a calculator? How would we, find this total distance without using that technology? Okay, so for us, what's important is we need to know when it travels left and when it travels right, because we're going to have to set up maybe multiple integrals on the time interval from 0 to 5 to represent when it goes right, when it goes left. Okay, so what we want to start with is maybe down here, figuring out what the velocity equation looks like. So differentiating the position function, we end up with this equation. Okay, now if I had a calculator, I would certainly type that into y1 and see what the graph of velocity looks like. If I don't have a calculator, well, that just requires me to use my background in algebra. So I know it's quadratic, it opens up. I could find the x-intercepts by setting the velocity equation equal to 0 and finding out where the velocity is 0, where the particle's maybe not moving. Okay, so real quickly in doing that, if the velocity is 0, and I factored out a 3, make the numbers a little easier to work with, continuing to factor without a calculator, okay, I would end up with this result. Setting each of these two variable factors equal to 0, I'm going to get 2 times at which the velocity, the derivative, is 0. Okay, so this is my velocity equation, and it's velocity versus time. So at time equals 1 and time equals 3, my velocity is 0. So I know the particle's at rest at those 2 times. I can continue sketching the graph by allowing t to be 0, and my y-intercept is 9, so I know up here is 0, 9. And from here I know that the graph of this quadratic opens up, so it probably does something like this. Of course that does continue upward, it doesn't curve back down. Anyway, So this is our velocity equation, and we only want to consider up until we get to, say, 5, because that's the time interval. Okay, so for us to find without a calculator the total distance traveled, we would have to pay attention to the fact that the velocity is positive here, which means this whole space right here represents how many steps the particle took to the right. So he's going right, 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 and then when his velocity becomes negative, he's turning around and going back left, and he continues going left while the velocity is negative below the x-axis. So these are the amount of steps he traveled to the left. Okay, he's still going left, 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 but his velocity is going to 0. He's stopping, okay, and then his velocity becomes positive, so he turns around and goes to the right. So let's kind of restrict our view up until we get to 5. So this space right here would tell us how many more steps he traveled to the right. So he went right, left, and then back right. Right, so if we're trying to find the total distance traveled, and we don't have a calculator, okay, we need to view and peek in at the velocity graph so that we can set up multiple integrals that represent the distance traveled. So for me to find this answer without a calculator, I'm going to rewrite it with different integrals. So the total distance traveled is going to equal the steps traveled from 0 to 1 to your x-intercept, 0 to 1, okay, of the function 3t squared minus 12t plus 9 dt. I think that's a t in there. Okay, now right here, he's traveling to the left, so the value of this integral is going to be negative, but I want it to be positive. So what I can do is I can subtract, instead of add, the value of the integral from 1 to 3. So we know that the value of this integral is going to be negative, so by subtracting that negative, it becomes positive. All right, now we need to look at from 3 to 5. Okay, the particle turns around and goes to the right, so that's going to require its own separate integral. We're going to add it because it's already going to be positive. Okay, so for us to find the total distance, that would require us evaluating all of these integrals. Okay, so I'm going to come down here. I'm going to find the antiderivative. So t cubed plus reverse power rule here, increased to 2 divided by 6t squared. Looks like we're going back to the position function. Okay, plus 9t. All of that evaluated from 0 to 1. So we have some work to do here. Minus, okay, so now we're going to evaluate this integral. T cubed plus 6t squared plus 9t evaluated from 1 to 3. Plus, and then the final one. But evaluated from 3 to 5. So a lot of calculations to be performed here. So in order to save some time, I'm just going to go ahead and give you the values after the calculations are performed, after you plug in 1 everywhere for t and 0 in for t, and you find that change. So this is 4. So this space is 4. We have the subtraction. The value here is going to be negative 4. Okay, so this space is also the same. Okay, and then plus the final integral or evaluation here was 20. So adding all that together, we get 28. So total number of steps traveled, 28. Okay, we don't have any units, so we can't really put any units on here. If you wanted to put just the word units, that'd be fine. But 28 is the answer. Okay, so look at number 98. Okay, notice that you're asked the same question. This is the new position equation on the same time interval. What's the total distance traveled? Well, again, if I have a calculator, I'm going to find x prime, the velocity, and I'm going to find in y1, I'm going to type in absolute value of that equation, go to the home screen, do the calculations, and it'll take care of the situation of when it traveled left and when it traveled right, because the absolute value, if you think about it, the absolute value of velocity back here, maybe it's worth noting, the absolute value of the velocity would take anything that's negative and it would make it positive, and then it would go in and accumulate all those positive regions. So the calculator takes care of that for you, but without a calculator, we need to know the x-intercepts on the velocity graph to know where to break up the integrals so that we can subtract the appropriate integral that for the region that falls below the x-axis. All right, so for this new position equation, we have our challenges cut out for us as far as finding the derivative. Worth noting here for this problem is you could FOIL this binomial and then distribute it with this binomial to where you get a bunch of terms, and then you can differentiate using the power rule. That's one way. Or you can see this as the product of two variable factors and use the product rule for differentiation. So I think that's how I'm going to proceed. So that's a good review at this point of the product rule. So it's the first term times the derivative with respect to t of the second term. I'll come back and take care of that. This operation means we have action to be performed. First times derivative of the second plus the second factor times the derivative with respect to time of the first factor. So more work to be done because of those derivative operators. Okay, so bring down the factor t minus 1. Okay, what you might notice here is this is the chain rule. Again, you could FOIL and differentiate term by term, but I'm going to go ahead and do the chain rule. So the outside function is t squared, so bring the 2 in front. Leave t minus 3 alone. Multiplying by the derivative of the inside function, which is just going to be 1. So I'll go ahead and put it here on this line. That's the derivative of t minus 3. Plus, moving on, quantity t minus 3 squared, this derivative is 1. Alright, coming down here, cleaning it up, all of this is being multiplied, so I think I'll just pull the 2 in front and then follow with the t minus 1 and t minus 3 factors. 2 doesn't get distributed with this one too because it's just all a product. Okay, right here. Okay, now for us where we're at, this is the velocity equation. Okay, we would want to graph this to know where this graph possibly is positive and negative so we know how to break up our integrals so we can subtract the necessary integrals for the regions that fall below the x-axis. Graphing this is going to be a little bit of a challenge in this format. But let's return to some algebra. Let's take this equation and put it in completely factored form. That way we can find the x-intercepts and quickly graph this quadratic equation. We know it's quadratic because this produces a quadratic and we collect it with another quadratic. Alright, but to graph it in this form is a little difficult, so we're going to completely factor it, meaning look at this term and this term. Okay, these two terms share the common factor of at least a t minus 3. And I'm just going to change to a bracket because too many parentheses get confusing. Okay, I'm going to pull out a t minus 3 factor, divide it out, leaving me with 2 quantity t minus 1. Now I'm going to travel over here, pulling 1 out from 2 factors that are the same. I'm left with 1. So just doing factoring. Alright, I'm going to clean up what's in the bracket. I'm going to go ahead and change back to a parenthesis. This is 2t minus 2. I want to now distribute so that I can collect with the t minus 3. So the good part about this problem is just that the derivative was challenging and then now putting it in factored form. Otherwise, if I had a calculator, back up here where I found the derivative, I guess which was right here, I'm typing that into y1 and looking at the picture of this velocity graph from x min 0 to x max 5. Almost there. Quantity t minus 3 times 3t minus 5. Okay, so this is quadratic. If I set it equal to 0, the velocity, I have 2 times at which the velocity is 0, which the particle is at rest. It may be changing directions, it may be not. So either t is 3, or t is, if this is equal to 0, 5/3. Okay, so just getting a visual of what we found for the velocity equation here. A lot of algebra, but all good stuff. Okay, for this velocity graph, which is quadratic, 5/3 is what? 1 2/3. So 1, 2, 3, 4, 5. So 1 2/3 would be about right here, and 1, 2, 3 would be here. If I wanted to find the y-intercept, I would have to distribute here, or maybe not. I can see that if I were to FOIL, I would get a plus 15, okay, and everything else would have a t in it. So it looks like my quadratic might look something like this. I know it opens up, so I'd have a positive coefficient, and it probably looks something like that. So all that work, product rule with chain rule, putting the equation in completely factored form so we can get the zeros, all that work, and we have a velocity equation that looks similar to example 1. All right, back to our objective. Okay, so how are we going to find the total distance traveled from 0 to 5 without using absolute value? Well, now that we have a picture of the velocity graph, we know how to set this up. Okay, so this is how far traveled right, how far traveled left, and at 5 I'm going to draw up to the graph and consider that the particle went back right here. So like the last example, from 0 to 5/3. And here, just to save time, I'm just going to put the notation x prime of t dt. Okay, the velocity now becomes negative, so I want to subtract the integral from 5/3 to 3 of x prime of t dt. In the final integral, I need 3 of them, 1, 2, 3, would go from 3 to 5. And I'm just using the notation for the derivative x prime of t in the integram position here, instead of having to say FOIL that, you know, and rewrite it 3 times here. Okay, so for the remainder of this problem, you know what would need to take place according to the last example, and if we did that by hand, okay, we would be successful in getting the total distance traveled. Okay, so that final answer works out to be a decimal, and it's 27.37037, where 7's been rounded. Okay, and that's units, since we weren't given any. Okay, so whatever the value of each of these integrals is, when we collect them all, this is the final result of the total distance traveled. Okay. So in the next video, we'll look at the remaining 2 problems, 99 and 100.